Today we're going to look at the relationship between continuity of a function and the differentiability of that function. So there is an alternate form of the limit definition of a derivative, which we've actually seen on our homework already. But this alternate form can be very useful in investigating the relationship between differentiability and continuity. It's a little bit less cumbersome way of looking at it. And that alternate definition is f prime of c is equal to the limit as x approaches a of f of x minus f of a over x minus a. Notice that this is just the slope formula between the points with x coordinate x and x coordinate a. So we have the points x f of x and a f of a. Those are the 2 points we're finding the slope between. And so this is similar to the delta x or delta h definition, because if we want x to approach a, that means this value is going to approach 0. So it accomplishes the same thing. The distance between the 2 points approaches 0, okay? This is a much more helpful way to look. Remember, if this limit is going to exist, that means that both the left-handed limits and the right-handed limits both exist. What does that apply? If the limit as x approaches a of f of x exists, based on what we know, is that that means that the function must be continuous at x equals a. So we can make that assumption about this function, okay? Now, here's what is also important to know. If a function is not continuous at c, then it cannot be differentiable at c. That's really, really important. I'm going to say it again. If a function is not continuous at a specific value, then it is automatically not differentiable at that specific value, okay? For example, if we look at this function here, since this function is not continuous at x equals 2, that means the function is not differentiable, meaning we cannot take the derivative at x equals, that's -2, not +2. Okay? So, if we look at example 6, we want to determine the continuity and the differentiability of this function. So let's first start by thinking about continuity, okay? Now, we have to discuss a lot of stuff here, so there's going to be a bit to write, so that's why I'm writing small. So our 3 conditions for continuity at x equals 2 is that f of 2 has to exist, which it does, it's equal to 0. The limit from the left and the limit from the right have to both exist. Now, don't forget that when we have an absolute value function, that is a piecewise function in disguise. The vertex is going to be at 2, so that's the point where it splits. So that's the function that we need to be working with. So we can see by doing that the limit from the left and the limit from the right are both going to equal 0. Whoops. Hang on. There we go. So here's our second condition of continuity then. We know that the left-handed limit and the right-handed limit as x approaches 2 both equal 0, and that means that the limit in general as x approaches 2 of f of x is going to equal 0. And since those two things are equal to each other, then the conclusion that we can draw is that f is continuous at x equals 2. So that's the first thing that we're interested in. Now we need to think about the differentiability of this function, okay? So similarly, we need to look at the limit from the left and from the right. We need to see, does the derivative from the left equal the derivative from the right? And so now let's look at the differentiability. We're going to use that alternate form of the limit definition. It makes it a little bit easier to work through. So if we look at the limit from the left, We need the limit as x approaches 2 from the left of f of x, which from the left is this side, so negative x minus 2, minus f of a. F of a is going to be 2 in this case, so if we plug in 2 to the right piece, we're going to get 0. We've already figured out f of 2. Even from the left, it's going to be 0. Over x minus a, which is going to be x minus, again, a is 2. If we think about what happens here, the 0 is really irrelevant. So we have negative x minus 2 over x minus 2. These divide out, but they leave a negative behind, and so the answer here is negative 1. Now let's look at the limit from the right. The limit as x approaches 2 from the right is going to be x minus 2 minus 0 over x minus 2. Again, the minus 0 is irrelevant. These divide out exactly, and they equal positive 1. Since these two values right here are not equal to each other, that means that the limit as x approaches 2 of f of x minus f of a over x minus a, or 2 in this case, does not exist. What we're essentially saying is the slope from the left does not equal the slope from the right, which we know based on what we look at when we look at the graph of an absolute value function. So the conclusion that we can draw here is that f is not differentiable. I'm going to use my little abbreviation here, at x equals 2. That's because the limit from the left, that says x equals 2 right there, does not match the limit from the right. The graph of an absolute value function looks like this. It's a V shape, okay? And actually, if we look at this particular absolute value function, it's going to have a vertex at 2, so it'd be more like this, okay? Again, the derivative represents the slope at a certain point. So if we consider the slope as we approach 2 from the left-hand side, the slope there is negative 1. The slope as we approach from the right-hand side is positive 1. Those are not the same, which means we can't determine a single slope value at the point x equals 2. What you can do visually, if I just give you a graph and ask where is it not differentiable, you are looking for a sharp turn on the graph. Anywhere that the graph does something like one thing and then switches to something else. This is called a corner or a cusp. Any of those sorts of things that happen, the graph is not going to be differentiable at that point because the slope values on the left will not approach the slope values from the right. If you need to formally justify your answer, then you need to use the formal definition of differentiability and look at the limits. But if all you're doing is a visual inspection of the graph, then you know that what you're looking for is either a point that is not continuous or a point where you have a sharp turn, okay? So those are sort of the clues that we are looking for. So if we look at example 7, the question is this function continuous or differentiable or both or neither at x equals 0? So continuity, we can go through the formal definition, but I think we've got that down now. We know that f of x is, continuous at 0. We know what the graph of a cube root function looks like. It looks like this. And so there's no asymptotes or holes. This is continuous at x equals 0. And we could use the formal definition of continuity to prove that, but in the interest of time, I'm not going to. The differentiability at x equals 0 is in question. Now, this is a different case. We don't have a sharp turn there. The question is, what is happening? Well, let's discuss the limits. We know that the limit from the left, so the limit as x approaches 0 from the left would be x to the 1/3 minus 0 to the 1/3, which is 0, over x minus 0, okay? This ends up, remember, this x is to the first power. These zeros don't matter. So if we simplify x to the 1/3 over x to the first, that gives us, the limit as x approaches 0 from the left of 1 over x to the 2/3. Well, that is a number over 0, so that limit does not exist. It doesn't matter what happens from the right because this limit does not exist. So since we don't get a value for that limit and the limit cannot exist, this function is going to be not differentiable at x equals 0. Now, why would that be? What happens when you have a slope of a tangent line that is 1 over 0? What this means is we have a vertical tangent line. That has undefined slope. That's why we can't find a value of the derivative there. And the reason is, if we were really precise in drawing this graph, it goes like this and gets very, very flat, and you end up getting a vertical tangent line just at 0. And so that's why this one is not differentiable, okay? Here is a theorem that is critically important moving forward, because from here on out, very rarely are they going to tell you that a function is continuous. Instead, they're going to tell you that it's differentiable. And differentiability implies continuity. The reverse of that is not true. We just saw a counterexample of that. Just because a function is continuous does not mean that it is differentiable. But if we know a function is differentiable, that implies that it must be continuous, okay? So again, let's refresh on what those requirements are. A function is continuous at c if f of c exists, the limit as x approaches c if f of x exists, and those two values are equal to each other. That's the definition of continuity we've been working with. We've now added differentiability today. So a function is differentiable at x equals c if the limit from the left and the right, using that alternate limit definition, or the other one, but this one's easier, gives you equal values. So we have to look from the left and the right of whatever that value is that we're interested in. And then as a side note, remember that what we are looking for is no sharp turns. So that's if you've got a multiple choice question or something like that, that's a good thing to look at. But anytime it asks you to justify, you must show the limits. That's the only way that you can analytically justify that. Sharp turn is not a thing. Let's look quickly at these last two examples. I'm going to leave the third example for you to look up on your own. So example 1, we're given the graph of f prime. That's so important. You need to make sure that you realize that we're looking at the graph of f prime, not the graph of f. So given the graph of f prime below, find the following if possible. So can we find f prime of -4? Well, this is the graph of f prime. So f prime of -4 would mean go to -4, look up on the graph, and see what the value is. And at this point, the value is 1. So f prime of -4 equals 1. Similarly, see if you can figure out f prime of 3. F prime of 3, when x is 3, f prime is equal to 2. So we can determine both of those things. Now they're asking us about those two tick marks mean we want the second derivative. So we want the derivative of f prime. F double prime of -4 and f double prime of -3. Remember, the derivative represents the slope. So looking at the graph, what's the slope of the segment where x is equal to -4? That's this segment right here. That has a slope of -1/2. Okay, so f double prime of -4 is equal to -1/2, because that's what the derivative represents. However, f double prime of 3 occurs at a sharp turn. So we can say that that one, and really if I'm being very precise, we should not use an equal sign here because you can't equal D and E. But f double prime of 3 does not exist because the function is not differentiable at that point. How do we know? Just by looking at it, because there's a sharp turn right there. If this had said to justify your answers, then you would need to discuss that the slope from the left does not equal the slope from the right, okay? So now if we want to look at example 2, determine if the following function is differentiable at x equals 2, what we need to look at is those two limits. So we need to look at the limit as x approaches 2 from the left of the limit definition, f of x minus f of a over x minus c. We need to look at the limit from the right of f of x minus f of a over x minus a. So put the video on pause for a second and see if you can set that up for yourself. These are the two limits that we should set up. F of x in the first case is x squared plus 1. F of x to the right of 2 is 4x minus 3 minus f of a. A is 2, so we're going to plug that in for the x's, over x minus a, which is 2. So we can do a little bit of simplifying here. When I subtract, I get the limit as x approaches 2 from the left of, it's going to be x squared minus 4, which means I'm going to get x plus 2, x minus 2 over x minus 2. These will divide out, and so from the left, I get 2 plus 2, which is 4. From the right, I'm going to get the limit as x approaches 2 from the right. That's going to be 4x minus 8. Those have a 4 in common, 4x minus 2 over x minus 2. These divide out and just leave us with a 4. Since those are equal to each other, the conclusion we can draw is that f is differentiable at x equals 2. So I would suggest that you turn the page, try the last example there on your own. Think about what you would need to know. The last example is to determine the values of a and b. We've done ones like this with continuity. So see if you can set that one up on your own, and you can check your answer against the PDF notes. Make sure that you get that copied down, whether you do it yourself or look it up. See you later.